Yeah, welcome back to chapter 4 of the Supplementary Coding Along series for the Build a Large Language Model from Scratch book. Here in chapter 4, we are going to implement, finally, the GPT model that we are going to pre-train and fine-tune in upcoming chapters. So this chapter is focused on coding the LLM architecture that we are going to use in upcoming chapters. Just to show you where we are in the grand scheme of things. So before we already implemented the data preparation and sampling where we had token IDs that we embedded into a multi-dimensional embedding space. And then also in the previous chapter, we implemented the attention mechanism. It's essentially the engine of the LLM that does the core computation. Now we are going to complete the architecture. So if you think of the attention mechanism as, let's say, the motor of a car, you can think of this one now as putting on all the remaining parts, the wheels, the steering wheel, and everything else around the motor, basically, the seats and so forth. So let's do this in a gentle way because, it's a big topic to implement a whole LLM architecture. So I think the best way to understand what the architecture looks like is to show you a dummy class. So here this dummy class is coding some placeholders, and we will be later on replacing these placeholders by the actual code. I think I also have a figure here somewhere that might be helpful. So just to show you again where we are in this book. So previously, again, we tokenized text, we had the token embeddings, and now we're going to implement this core model here. And in this figure, I see this one. So what you can see here is the GPT model that we are going to implement. And so it receives tokenized text, and then the embedding layers, we already coded them in the previous chapter, but they are technically part of the model. So we have these embedding layers, which you can see here. So we have the token embeddings and the positional embeddings. They were covered in chapter 2, where we had a mapping from the token IDs to an embedding dimension that we can define. And the input size of the embedding layer was the vocabulary size, all the unique words in the training corpus. In the positional embeddings, they had the context size, so how many tokens can fit into a context. We had a very simple one, only six tokens, I think, in chapter 2. But in reality, this could be, for example, 256, 1024, and so forth, depending on how much context we want to support in the LLM. And then now we are going to add a few more things. So let me show this also in the context of the figure. So one of these things is the transformer block. So and an LLM consists of multiple of these transformer blocks, and each of the transformer blocks has a number of elements that we will talk about later in this chapter. But one of the core elements is the masked multi-head attention module, which we implemented in the previous chapter. And then we are going to add some output layers, and that is essentially how the LLM architecture looks like conceptually. Now, going back to our dummy GPT model, this is coding what I've just shown you in the figure. So we have these embedding layers, we have optionally dropout, and then here is this transformer block. And like I just mentioned, it gets repeated a number of times. So here we are going to repeat it a number of times, where the number of times is specified by n layers. So CFG stands for, it's just short for configuration. So this is a Python dictionary, as I will show you later, that contains some configuration. Maybe I can actually just add it here so that it's more clear. For some reason, there we go. Here. So we have a vocab size. This is the number of unique tokens in the input. Also in the training set. So this is based on the GPT-2 tokenizer that we are using from TickToken. Then we can specify a context length, how long the context is that the LLM can support. Here we are choosing 1024, but modern LLMs, they can also support longer context sizes. However, it also depends on the hardware, what your hardware supports. So the longer the context size, the more expensive the computation, and the more hardware requirements you need. The embedding size, this is the embedding size for the token embeddings. So previously in chapter 2, we talked about 3-dimensional embeddings. Now we are going to scale this up to a bit larger, 768. the number of heads in the multi-head attention module that we implemented in the previous chapter. Here, the number of layers, it's called, n layers, but it really refers to the transformer blocks, how many transformer blocks we want to repeat, the dropout rate, and whether we want to use the bias in the query key and value linear layers. And this is just a configuration file that we are going to pass as a CFG into this dummy model. The reason why I'm calling this as a CFG is to keep it short so it doesn't go off here in the cell and becomes too long, because otherwise it would be harder to read. And so we have these transformer blocks. And then we have something called a layer norm here. We will get to that later. And then we have this output layer. And so you can see what's interesting is the input layer maps from the vocabulary size into the embedding space. And then the output layer maps back from the embedding space to the vocabulary size. So this will allow us to generate words, because what we're doing is we're transforming the token IDs, the words, into an intermediate representation, the embedding space, like a vector representation. And then later on, we will transfer them back into this original vocabulary size space, back into token IDs, essentially, so that the LLM generates text. So these are the elements, and here in the forward method we are going to use these elements. So we create the embeddings, we add dropout optionally, then we apply the transformer blocks. So when I call this one, thanks to this sequential, it will put it through all the different transformer blocks. And then we have the output layer here. So if we consider this as our LLM, this looks very simple because we have these placeholders. But just to make this work in the case of the video, before we fill in the placeholder with real code, I have also placeholder code. So you can see for now I'm calling this the dummy transformer block, and it's really not doing anything. It's just returning the input. Later, we will fill this block with actual code that will explain what the transformer block does exactly. But as you already have seen here, one part of the transformer block is the masked multi-head attention module. So we will add that later on here and a few other things. And then layer norm, we will also discuss that separately. It's essentially a normalization layer that gets used both in the transformer block and here essentially. But these are details for now. Just think of it as the big picture concept, and we can already use this. For example, if we have some inputs here, so we are using the tick token tokenizer from chapter 2, we are loading it here, and then we create a small batch here. So the batch is, I can just show it to you. I hope it works. Yeah, there we go. So the batch is consisting of 2 inputs, 1 and 2. And so the first input text is every effort moves you. And the second input text is every day holds A, and then so forth. And the task of the LLM is to complete this input text. So we can see this is the first text. We have 1, 2, 3, 4 tokens. So in this case, each word represents a token. It's not always true. Sometimes a word gets split into multiple tokens, but to keep the example simple, I chose words where each word is exactly 1 token. Then we are here using the tokenizer to encode it, turn it into a tensor. And so what you're seeing here are the token IDs corresponding to these texts. So this is an input that our LLM will receive during training, and then the task is for the LLM to generate or predict the next word in this text when we are pre-training it. Pre-training will be the topic of the next chapter, so here I'm just explaining what the input and output looks like. So here we are now initializing a new dummy GPT model using the configurations I have specified here. So this would be really, we can also make it more clear. This would be this CFG that you are seeing everywhere here, this dictionary. And then we can already use the model. So the model is initialized with random values for the layers, the embedding layers, and later we will also have, we already have a linear layer here. So similar to before, these will be initialized with random values, and those will be trained later when we are optimizing the LLM. So that is initializing the model, and then here we are calling the model. And the output of the model, they are usually referred to as logits. So it's like a deep learning jargon, but in deep learning, in the field of deep learning, the last layer, the last linear layer that returns the outputs of the linear layer, those values are referred to as logits. I taught statistics classes. I was a statistics faculty a few years back. It feels like a lifetime ago, but this was, there's a lot of theory, or not theory, but like there's a reason why it's called logits. It's something I have also videos for if you're interested, but for now, just refer to it maybe as, or think of it as the last layer outputs before we pass it to any other function. So we have not defined this one, of course. It's a recurring theme here in these videos that I forget to define or execute some cells. So what you can see here is a very large tensor. And this tensor is 2 by 4 by 50,257. And so the reason for this dimension is, we have 2 inputs. So here I can maybe show this for reference. Batch.shape is also 2 rows, so that is where the 2 comes from. And then we have the 4 tokens in each column. So here that's the 4, but now we have 50,257. So these are the logits for each of the tokens, essentially. So this dimension comes from the fact that we have an output layer here that generates this vocab size. So each token, before each token was represented by, here in this case, 768 dimensional vector. In chapter 2, we used a 3-dimensional vector. So that is what goes in. And then what comes out here is the same as the vocabulary size. It's a 50,257 dimensional vector. So this sounds like complicated. So how does that turn back into token IDs? So for that, we will actually look at this closer in chapter 5. So what we have to do then is we have to optimize the LLM. We have to train the LLM, and the LLM will learn that the next token it tries to predict. So if we give it this input, the vocabulary token ID corresponding to this one will have the largest score in this logits vector. And then we extract the largest score, get the token ID, and then we turn it back with our decode method. We replace encode with decode. We replace that into a word, so the token ID to a word. But this is already maybe too much detail because this will be covered in chapter 5. For now, just consider we are generating some values here. So we are generating these 50,257 dimensional vectors for each of the token IDs, and we will take care of them later once we have trained the LLM. But I hope so far you have a good understanding at least how the architecture looks like, so that we have this GPT model where it receives tokenized text, then it goes through embedding layers, we have these transformer blocks, and then we have this output layer that produces these 50,257 dimensional vectors, which are for now just placeholder values, and later on we will fill in the details. And in the upcoming videos we will also fill in the details in terms of what goes exactly on in this transformer block.
Get this book at Manning.com.